September 12, 2025. Astronomers spot something impossible. A colossal object streaking in from deep space, its tail stretching 5 times the width of a full moon, dwarfing anything seen since Oumuamua. Within hours, a second visitor is confirmed. Both racing toward the sun for a close pass mere weeks apart, yet arriving from opposite corners of the sky. The odds of this cosmic double entry are, according to experts, astronomical. The official story, twin comets. But the evidence points to something deliberately engineered. A bigger mystery object now entering our solar system with a mission nobody can explain. Is this an interstellar accident or the first move in a secret operation that's been triggered by us? The answer starts right here. On September 12, 2025, the SOHO spacecraft's SWAN instrument caught something that stopped astronomers cold. A new object, bright and unmistakable, blazing through the solar system. Within hours, the first data poured in. A tail stretching nearly 2.5 degrees across the sky, which is about 5 times the width of a full moon. That kind of scale is unheard of for a newly discovered comet. Initial photometry put it at magnitude 7.4, bright enough for small backyard telescopes and even some binoculars. The news spread fast and amateur astronomers scrambled to confirm what the satellites had picked up. In Australia, just 2 days after the satellite alert, an observer captured a dramatic image of the object. A streak of light so long it threatened to spill out of the camera's field. By September 13th, the International Astronomical Union had made it official, naming the object C/2025-R2 with the tag SWAN in recognition of the instrument that first spotted it. Within a weekend, both the professional and amateur communities were locked onto this thing, trading images and brightness measurements across hemispheres. The sheer size and brightness set off a wave of speculation. Most comets discovered in the modern era are faint, often requiring powerful telescopes to see at all. SWAN, on the other hand, was visible to anyone who knew where to look. Its tail slicing through the constellation Virgo and growing brighter as it drew closer to the sun. The initial reaction wasn't just excitement. It was disbelief. This wasn't just another icy visitor from the outer reaches. The numbers didn't fit any recent precedent. As the reports piled up, one thing became clear. SWAN was physically dominating the inner solar system in a way that hadn't been seen since the days of Hale-Bopp or even further back. The amateur community, often the first to spot changes in brightness or odd behavior, was already debating what could possibly drive a tail this long and this bright. For now, the object was simply too big, too vivid, and too fast to ignore. And as the world's telescopes tracked its path, the question shifted from what it was to why it had arrived now, and whether its timing was just the first part of a much stranger puzzle. C/2025-R2, now officially known as SWAN, is not the only newcomer drawing attention this October. Just days before its discovery, another object 3I/Atlas was already inbound, making its own approach from a completely different sector of the sky. SWAN's path traces back through Aquarius, while Atlas entered from the direction of Sagittarius. On a star map, these two arrival vectors are separated by more than a quarter of the celestial sphere. Yet both objects are set to reach their closest point to the Sun perihelion within the same 10-day window. For SWAN, that moment comes around October 20th at a solar distance of about 150 million kilometers. For Atlas, it is October 17th, just 3 days earlier, skimming past the Sun at roughly 203 million kilometers. That puts their perihelion points only about 50 million kilometers apart, closer than Mars ever gets to Earth. This is not just a matter of overlapping dates. The geometry is striking. Both objects are on steeply inclined orbits, with SWAN's path tilted more than 60 degrees off the ecliptic and Atlas nearly perpendicular to the plane of the planets. Their approach angles are so different that by chance alone, the odds of both crossing the inner solar system at almost the same time and at such similar solar distances are vanishingly small. Astronomers who track long-period comets and interstellar objects are used to random arrivals scattered across the calendar with perihelia spread out over months or even years. But here, the two brightest new objects of the decade are converging on the Sun in near synchrony, each from a different corner of the sky. The timing adds another layer. As both SWAN and Atlas sweep through their closest solar approach, Earth's telescopes are effectively blinded. From October 8th to 18th, the sun's glare blocks direct observation, creating a blackout window that covers the critical days when any unusual behavior would be most visible. That means the moment of closest proximity both to the sun and to each other happens just out of reach, with no way for ground-based observers to watch events unfold in real time. To get two such objects from such widely separated origins, hitting perihelion within days, and at nearly the same solar distance, all during a period when the sun itself shields them from view, defies the usual expectations of chance. In the language of orbital dynamics, this is a corridor, a narrow window in space and time that both objects occupy together. Whether it is coincidence, a hidden link, or something engineered remains an open question, but the geometry alone is enough to make even the most skeptical astronomer pause. 3I/Atlas first drew attention not for its brightness, but for the way it broke the rules. Early spectrographs from the Atlas Spec Lab group reported something that set off alarms: a body dominated by nickel with virtually no iron in the mix. That runs counter to everything known about comets, which almost always show iron-nickel blends in their vapor. The claim was so unexpected, some labs immediately called for the data to be rechecked. A calibration controversy that spilled onto astronomy forums and triggered a wave of independent reviews. The debate only intensified with the next round of measurements. Instead of the classic water vapor signature, 3I/Atlas's Comet pumped out carbon dioxide at rates 5 times higher than water. The 4.3 micron CO2 line dominated every spectrum, while H2O barely registered above the noise. That's rare, but not unheard of in cold origin comets. What couldn't be explained away so easily was the behavior of the tail. Observers tracking Atlas's motion noticed a pattern. 3 distinct accelerations, each spaced about 2 weeks apart, each coinciding with a sharp change in tail color. The first pulse was logged on July 29th, the second on August 14th. Photometric data showed a sudden jump in brightness, while the spectral slope shifted from reddish to nearly neutral, then back again. These so-called delta V pulses weren't smooth like the gradual push from solar heating. They came on fast, then faded as if the object had fired a thruster. Peer reviewers pushed back, pointing to the risk of calibration drift or hidden systematic errors. But the Atlas Spec Lab team defended their findings, arguing that the timing and magnitude of the pulses matched up across independent observatories, from the Ibero Tracker Network to Bill Gray's Distributed Telescope Array. The numbers didn't behave like typical outgassing. The tail's CO2 mix seemed to modulate in sync with each acceleration, a phenomenon some called thrust mix modulation. What really set the rumor mill spinning was the energy estimate. If the observed accelerations were real, the implied power source inside Atlas would need to deliver something on the order of 10 gigawatt, about the output of 10 large nuclear plants. That's far beyond what any known comet nucleus can muster. The mainstream view still holds that natural processes can account for most of the data, but the gaps, especially the nickel-only spectrum and the stepwise accelerations, have kept the engineered object hypothesis alive. For now, the Atlas anomaly file remains open, with each new dataset fueling both skepticism and speculation. C/2025 R2, now simply called SWAN, stands in a league of its own. The numbers tell the story. A tail stretching 2.5 degrees, a brightness peak that rivals the best comets of the last century, and a core that, if the wildest estimates are even close, could be pumping out 10,000 gigawatt of energy. That's more raw output than the entire power grid of Earth and then some. But it isn't just the scale that has people talking. It's the claims coming from the fringes of the astronomical community. Claims that SWAN is armored, shielded, and powered in ways that stretch the limits of current physics. The first whispers started with the reflectance data. Standard comet nuclei scatter sunlight in a predictable way, but SWAN's core reflects light with a sharp metallic signature. Some amateur spectroscopists argue this matches not just nickel, but a nickel-cobalt blend, materials chosen on Earth for their strength and resistance to corrosion. The term nickel-cobalt hull began circulating in chat rooms and late-night podcasts, fueled by the object's stubborn refusal to break apart or dim as it closed in on the sun. Then came the reports of an optical anomaly, a persistent silvery halo around the nucleus, shifting in pattern and intensity. To some, it looked like a plasma envelope, a kind of electromagnetic shield that could deflect solar wind and cosmic debris. That's where the fortress nickname comes from. Unlike 3I/Atlas, which acts more like a drone, quick, agile, and oddly efficient, SWAN presents as a tank, slow, steady, and seemingly invulnerable. The tail, already record-breaking in length, pulses with micro-thrusts that defy simple outgassing models. Photometric analysis shows tiny rhythmic changes in tail direction as if the object is making course corrections with precision bursts of plasma. Each pulse registers as a blip in the brightness curve, and the pattern repeats with a regularity that's hard to chalk up to random surface eruptions. The orbital numbers add another layer. SWAN is on a path that will take it around the Sun once every 22,554 years. A cycle so long it brushes up against the last ice age. The implication is staggering. If this object is engineered, it's been on a preset course for longer than human civilization has existed. And yet, it arrives now at the same time as Atlas in the same solar corridor during a window when Earth's telescopes are blinded by the Sun. The odds of all these factors combining by chance are vanishingly small. All this feeds into a growing sense that SWAN isn't just another comet. Its sheer luminosity, the hints of advanced shielding, the possible armored hull, and the scale of its energy output make it the most formidable object to enter the inner solar system in living memory. Whether it's a fortress, a probe, or something else entirely, SWAN has forced astronomers to rewrite the rules and open the door to theories that until now lived only in science fiction. Every major anomaly logged for SWAN and 3I/Atlas has turned the conversation from what these objects are to what they might be doing. When two massive bodies, one on a 22,554-year return, the other on a hyperbolic, possibly interstellar path, arrive nearly together, the odds of pure chance drop off a cliff. The timing, the geometry, and the blackout window have all fueled a wave of mission theories. One possibility looks almost routine, at least by cosmic standards, a scheduled maintenance or refueling run. In this scenario, the Sun acts as a pit stop. Both objects could be engineered to use solar energy or magnetic fields for recharging, data handoff, or even a systems audit. The idea isn't far-fetched in deep space mission planning. On Earth, solar flybys are standard for gravitational assists and energy boosts. If these objects are probes, the Sun is the logical place to top up or exchange information. Another theory is less peaceful. The close approach could be an intervention, a rendezvous to recover or neutralize a malfunctioning unit, or perhaps a contest between rival factions converging on a resource. The power levels estimated for each object, Atlas at around 10 gigawatts, SWAN at a staggering 10,000, suggest the kind of energy reserves needed for active maneuvering, not just passive drifting. Stepwise accelerations and tail modulations in Atlas and micro-thrust pulses in SWAN hint at a level of control that fits with a mission profile, not random outgassing. There's also the audit chain scenario. Oumuamua in 2017, followed by Atlas and now SWAN, could represent escalating responses to Earth's century of radio transmissions. Each new arrival would be a more complex probe sent to check in, gather data, or escalate contact. In all three frameworks, the Sun isn't just a backdrop. It's the power node, the rendezvous point, the beacon. The evidence doesn't settle the debate, but it does force a new question. If this is a mission, what's the mission for? A 22,554-year orbit is more than just a number on a chart. It's a cycle that reaches deep into the last ice age when the world looked nothing like it does today. Around 20,000 BCE, glaciers covered much of the northern hemisphere, and the climate was shifting in ways that shaped the earliest chapters of human civilization. That same epoch left its mark in the ice cores of Greenland and Antarctica, where layers of dust and tiny chemical changes hint at sudden dramatic events in the sky. Some researchers have pointed out that these layers line up with periods when bright long-period comets could have swept through, leaving not just debris, but stories that might have echoed down the generations. At the heart of this idea is a place called Göbekli Tepe. Göbekli Tepe, a site in southeastern Turkey, built more than 11,000 years ago. Its stone pillars are carved with animals and abstract symbols, but among them are motifs that some believe show the paths of objects in the sky, possibly even comets. A handful of theorists argue that these carvings record cycles far longer than a human lifetime, maybe even marking the return of something like SWAN. The mainstream view is much more cautious. Archaeologists and astronomers alike warned that these connections are speculative at best, built on patterns that could just as easily be chance. The debate is heated, with critics pointing out that no direct evidence ties these ancient monuments to specific astronomical cycles. Still, the timing is hard to ignore. If SWAN really does return every 22,554 years, its last swing through the inner solar system would have happened just as the world was emerging from the grip of the glaciers, at a moment when human culture was taking its first steps toward building monuments and tracking the heavens. Whether that's coincidence or something more is an open question, but it adds a layer of mythic resonance to an already extraordinary event. In the end, the story of SWAN isn't just about numbers or orbits. It's about the possibility that the sky's rarest visitors have always been woven into the story of our own beginnings. From October 8th to 18th, every major ground-based observatory faces a hard stop. Official schedules list the window as solar conjunction downtime, but behind the scenes, the restrictions go further. Internal memos from U.S. Space Command and the European Space Agency direct teams to suspend all radar and high-resolution imaging of both SWAN and 3IATLAS during this blackout. Some proposals for alternative coverage are denied without explanation. Requests for raw data are quietly rerouted or delayed. A handful of telescope allocation reviewers speaking off the record describe explicit orders to avoid public statements about either object until after perihelion. The result is a forced silence at the very moment when the two most unusual visitors in decades cross the sun's glare, leaving only a narrow band of independent astronomers and amateur networks to fill the gap. When the blackout orders hit, the official channels went silent, but the amateur networks did not. Bill Gray, a veteran tracker known for his open-source orbit calculations, started rallying a distributed web of backyard astronomers and small observatories. His call went out across public forums and encrypted chat rooms. Keep your scopes on the sky, log every flicker, and share the raw data before it disappears. The Ibero Tracker Collective in Spain and Portugal began pooling wide-field sensor feeds, while leaks from private astronomy groups suggested makeshift plans to bypass the blackout using radio telescopes and even repurposed weather satellites. With government agencies off the record and big observatories locked down, the grassroots effort became the only line of defense against a total information vacuum. Anyone with a telescope, a radio dish, or access to open-source tracking software could join. The blackout window wasn't just a challenge. It was an invitation. If you want answers, you're part of the search now. When SWAN and Atlas re-emerge, the first signals might come from someone's backyard, not a government lab. The facts are clear. Two anomalous objects entered the inner solar system together, defying statistical odds and raising questions no agency has answered.